My name is Tapasvi, and I'm a compiler engineer at Tenstorrent. So the topic I'll be presenting today is how do we model multi-device in a compiler? How does it actually work on the hardware? And how can end developers such as yourself be able to use our compiler and runtime stack? So let's begin with some motivation to kind of help prime the topic. So on the screen above, you can see a very simple matrix multiplication. We have these 4 blocks that are being matrix multiplied with this weight matrix per se, and it's going to produce this type of matrix on the right side over here. And the goal that we want to do is effectively parallelize this operation across 2 devices. So these 2 devices, and there's a couple of different strategies and ways that we can approach this. So the first thing that we can kind of prematurely do is we can split this matrix on its outer dimension. So AB blocks will kind of go to device 0, CD blocks will go to device 1, and we can see from our resultant tensor that A needs to get multiplied with 1, and B needs to get multiplied with 3, as well as 2 and 4. So effectively, both of these two A, B, and CD blocks need the entire weight matrix on both of the devices. So then what we can do is we can take our weight matrix and then we can replicate this weight matrix on both these devices. So now we can actually perform some useful computation on both these two separate devices. So once we do the matrix multiplication, we have AB being matrix multiplied with this weight matrix, and similarly on the right-hand side, it's going to produce this result over here, which is very similar to the final result that you see on the final output matrix. And then the device 1 is also going to produce the same exact result that you see over here. So just visually looking at this, you can see that the result matrix is split across its out of dimension on both these devices. So we can effectively combine both of these results or concatenate them on the outer dimension to get our final resultant matrix. So effectively, we've parallelized this operation across 2 devices. And this can be extended for various different other like convolutions, reshapes, etc., with various different degrees of complexity. So from this, we realized that we need some type of, first, we need a representation of a mesh of devices. So we need to know how many devices we have in our mesh, how are they kind of positioned or located. We had 2 devices in the previous examples, but when we have like 10, 20, 32, etc., it gets a lot more complicated. We need to be able to shard tensors across devices, right? So just as we sharded our inputs, we need to be able to shard that on different devices. We want to be able to replicate tensors, so replicating your weight matrices. And we also need to be able to compose tensors together or aggregate them across devices, like we did for our resultant matrix. Another way that we can actually split this is we can split the input matrix on the inner dimension. So AC blocks are going to go on device 0 and BD blocks are going to go on device 1. And in this situation, as if you see from the resultant matrix, you see that A and C only need 1 and 2 from the weight matrix, and B and D only need 3 and 4. So effectively, we can actually cut our weight matrix on the outer dimension and only put the relevant blocks that we need on both of these devices. So we save some space, and it makes some of the computation a lot easier. Once we do the matrix multiplication on this, we see that we get these resultant tensors that get produced on both these devices. Now, this is not as trivial as it was in the last example, but you can see that over here we have A1 should get added with B3, which is this element over here. A2 should get added with B4, and so on and so forth. So effectively, we've produced partial results, so partial sums, and we need a way to be able to add or sum both of these partial sums together. So what we can do is we can communicate between these 2 devices. We can send this matrix over to this guy and this matrix over to this guy, and then we can just do an element-wise addition on both of these partial sums, and that will actually give the resultant matrix that you have. And then you can use this resultant matrix in further computations, or you can query it off of the device, and that's your final result. So we learned from that last motivation that we need some way to communicate tensor shards across devices. as well as there's various different communication patterns that can be done, and we'll go over some of the most common ones that we use in the compiler stack. There's also various different types of parallelism strategies that the industry employs when it comes to ML models. So here's just a kind of dump of various different ones I was able to find online. Hugging Face has a fantastic write-up of various different types of these strategies with examples. These slides can be shared afterwards, and I highly recommend you guys to take a read at this one. The primary strategies that we employ are data, tensor, and pipeline. However, we are also experimenting on the other strategies as well. So to set the stage of like what each of these strategies are, or specifically the ones that we care about, for data parallel, we effectively are splitting our data, in this situation, our batch, across two devices. So our input tensor is as follows. We're going to split it across these two, and then we're going to perform independent computations and then aggregate the result afterwards. For tensor parallel, it's very similar to the motivation example where we're going to split the inner dimension of the input and the outer dimension of the weight matrix. So splitting some layers of the model itself, performing independent computations on both these devices, maybe doing some communication between both the devices, and then aggregating the results to get the final result that you need. And then finally, for pipeline parallelism, we have we're going to effectively split our input into a series of mini batches. So if anyone is familiar with any kind of pipeline parallelism in like common literature, this kind of works in the same way. We're going to split the input into this mini batch of 128 by 256. We're going to put this weight matrix on device 0, this weight 1 matrix on device 1, and effectively pipeline this mini batch, micro batch across both of these two devices. So once device 0 has computed its result, it'll send it to device 1, and then we can send in the next micro batch over, and so on and so forth. Any questions so far? All right, cool. Next, let's go over some of the multi-chip configurations that we have available at Tenstorrent. So I've seen many of you guys already use the N150 cards that we have. Those are single chip cards. We have a bunch of different multi-chip cards. So the very simple one is called our N300 card. This consists of 2 chips. We have a LLM box. This consists of 8 chips. So this is our desktop workstation. And we have our Galaxy server systems, which consist of 32 chips. And effectively, we can actually combine our galaxies into multiple galaxies. So you can kind of chain them together, 32, 64, 128, and so on and so forth. But for now, primarily in the compiler, we are focused on these 3 main configurations. All right, cool. Okay, so before we actually go deep dive into the compiler, it's important to understand how the actual runtime works and what are the runtime features that are exposed from TTNN that allow the compiler to do analysis as well as run a multi-device model. So the fundamental kind of unit of abstraction for devices in TTNN, which is the TT-Metal library, is something called the mesh, the TTNN mesh device. Here we have a representation of the devices that are available on our system. We can create meshes in various different shapes, 1x2, 1x8, 2x4, 1x32, 8x4, and their reverses as well. And all of these correspond to the different cards that you saw on the different screen, depending on how many cards you have. You can also create submeshes. So if you want, let's say in your 8x4 system, you want to create 4 2x4 meshes, for example, that is also possible. And that is something that's also being explored in both the compiler and the runtime side as well. Next is something called the TTNN tensor. This is the fundamental unit of abstraction of data in TTNN. The main things to know for this is specifically the tensor memory. So how is the tensor actually laid out on the device? There's 2 configurations or 2 types that we care about for multi-device, which is multi-device, which consists of the storage that is actually present on the device at any given time for a tensor, and multi-device host, which is the same kind of shards of storage that were on the shards of storage, but just on the host memory itself. So if you have a tensor that's split across devices, every single device is going to have some partial memory or storage for the tensor. And the TTNN tensor is going to provide kind of like a layer of abstraction that combines all of those shards and represents it to the user as a single tensor, but that has multiple shards across multiple devices. TTNN has a bunch of different APIs, device APIs that it exposes. So two of the main ones are open mesh device. So you can open a device cluster according to a specific mesh, and you can also close the mesh device. So anybody who's kind of already programmed using TTNN, this is very similar to your TTNN open device. You might have just blindly provided 0 up until now. But we can actually provide like a specific mesh that you want to open for your program. The next kind of important concept to know is something called mappers and composers. So similar to our motivation examples, we needed a way to be able to replicate a tensor to one tensor to multiple devices, shard a tensor across multiple devices, as well as concat a multi-device tensor into a single tensor. So TTNN provides abstractions for all of these in mesh mappers and mesh composers. And there's a bunch of APIs that they also provide for you to be able to create these mappers and composers with ease. So let's take a quick look at what this actually looks like in TTNN. So there's a very simple example. This is just a snippet of TTNN code. Here, I'm going to open a mesh device. I'm currently on an N300 system that has a 1x2 mesh. I create my torch tensor, which has this particular shape. And then what I'm going to do is I'm going to take this torch tensor and I'm going to replicate it across my 1x2 mesh to create a mesh tensor, which basically has 2 shards. Both of the shards are going to be of this size that live on 2 devices. So we can call this mesh mapper API from the previous slide. That will create this mesh tensor, which is a TTNN tensor, but it has 2 shards of this size that live on both devices. Similarly, we have the shard tensor 2D mesh. So this is kind of similar to the replicate tensor, where in this situation, we're using the mesh mapper abstraction. So over here, we're kind of doing the same thing where we provide this. We're going to create a mesh tensor. However, in this situation, we're going to provide the mesh shape that exists or that we've opened our device on. And something also to notice is we need to provide what dimensions we actually want to split our tensor across and in what axes of the mesh. So over here, you can see that in this example, we want to split this dimension over here, 256, across these 2 devices on this dimension over here. So we're going to basically take that 3, which is this index over here. It's going to correspond to the mesh dimension over here. And then on this mesh dimension, we are not splitting anything. So that's just represented as none. So what this will do, or the shape of this after you actually do this operation, you're going to have a 1x1 by 32 by 256 divided by 2, so 128. So every single device, so both your devices are going to have a shard of your original tensor of this shape that's represented by this standalone TTNN tensor. Similarly, we have the concat 2D tensor to mesh, very similar to how the previous slide was shown. Here, we spiced it up a little bit. We have a 2x4 mesh, so this is your LLM box. In this situation, I'm going to shard my tensor first. So I'm going to shard this guy, so this dimension over here, tensor dimension 2 across here, and tensor dimension 3, I'm going to shard it across the mesh dimension 4. Mesh axes over here. So effectively, I've sharded my tensor, and then I want to just concat it together. So this is a very trivial shard concated together. The same tensor before equals after. So we're going to provide this mesh composer, the same attributes of the dimensions of the tensor that we want to combine together. Yeah, and through this, we actually model all of this in the compiler itself. So we can use a lot of these abstractions and perform analysis on it. All right. TTNN also provides a bunch of different APIs. We use various different ones of these in the compiler. I won't go over all of them. This is just kind of a dump of the main ones that we used. Distributed tensor and aggregate tensor are two important ones that we use, as well as creating multi-device tensor. All right, before I continue, are there any questions? Check chat. Okay. Awesome. Great. All right, so the next kind of topic I want to go over is we went over how do we shard tensors, how do we replicate it, what are the abstractions in the runtime. The next thing that we need to do from our motivation example is how do we actually communicate tensor shards across different devices. And so luckily, the industry has actually been working on this for many, many years, and especially the HPC community has done a ton of research on this. So there already exists a lot of stuff that we piggyback off of and use in our TTNN stack. So our collective communication library is essentially the library of all the different collective operations that we support. There's various different ones that are currently in TTNN. We have all gather, reduce scatter, which are both currently supported. All reduce is in work in progress, and send and receive are also work in progress. These are your point-to-point communications between specific devices. So if anybody has used like NCCL, NVIDIA's collective communication library, it's very similar. Here's kind of a link that dumps that links to their library and how their implementation works, and we kind of follow similar patterns. All right, I see a question. How are we avoiding the synchronization overhead, or is there something shared memory across chips? Yeah, so this is a fantastic question. This goes very deep into TTNN, something I'm not too familiar of, but they have overlapped communication that occurs. So a lot of their operations trigger in async mode. So you can trigger off a particular communication that happens and start the next computation. But that's pretty much as far as to the depth of knowledge I have for that. Question for TTNN multi-chip library. Would the big picture goal be to maybe have some abstraction that automatically picks the appropriate mesh map or composer based on some hardware config or YAML or something? I'm not sure if I completely understand this. So the user has the ability to select or define what mesh map or composer that they want to use or do. As well, the compiler is also able to figure out what, if a user, let's say, has an operation and they want to kind of split it across particular devices, they don't actually have to program the composer or the mapper itself. They can provide some metadata, and the compiler can figure out what should the actual call look like. And so that the onus of that is on the compiler. Okay. All right. So to go over the communications very briefly of what they do, the three main ones. So all gather, we'll start off with all gather first. Here, let's say at timestamp 0, I have device 0, shard tensor, and device 1 sharded tensor. I'm going to communicate both of these tensors to both these devices. And then effectively, I want to concat both of these on dimension 0. So my final resultant tensor looks something like this. So 32, 1, 256, 256 on both these devices. This is very similar to our motivation example where we had these split sums, split results, and we wanted to combine them together. All reduce works in the same way where we have some communication that happens. We're sending both these sharded tensors across to both these devices. And in this situation, we're going to perform a reduction. So we can perform some type of element-wise reduction, such as summation or multiply or something like that. So the resultant tensor is exactly the same shape as your initial tensors, but just some reduction that's been applied on top of it. So from our motivation example, we wanted to sum these partial sums together. All reduce is basically the operation that you would execute in order to do this. Reduce scatter is very similar to all reduce. So effectively, we do the same where we send the tensor shards across, we perform the reduction. However, now we want to actually scatter the results to the remaining devices or various different devices. So in this situation, we've performed the reduction, then we want to scatter dimension 0 across both of these devices. So at the end of the day, both these devices have this split shard, and then you can do some other computations from the rest of your graph on top of this. There was a fantastic paper that was released in 2023 regarding CCL, like a whole industry-wide analysis of CCLs. What are the algorithms that are actually being used to implement them? In what situations do they really perform well, not perform well? I highly recommend anybody interested in this space to give this a read. It's a really great research paper. And TTNN does use some of this internally. However, I'm not sure of the exact implementation, underlying implementation of their CCLs. All right. Any questions so far? Great. Okay, so now let's get on to the compiler. All right, so the compiler that we have at Tenstorrent is called TT-Forge. TT-Forge consists of various different parts. So we have the front end parts of the compiler, the core TT-MLR compiler, and at the end of the day, what we do is we emit and we call TTNN C++ code. So all of the TTNN support that you saw for multi-device, we model in the compiler, and then we effectively call those operations using TTNN. Our TT-Forge compiler is based off of the MLIR infrastructure. And primarily for multi-device, we use JAX as the primary front end for running operations and models through the entire compiler stack. However, we're also exploring Torch using Torch XLA, as well as Forge front end, which is another one of our front ends directly into the Forge compiler itself. All right, let's go over some of the stuff that we do in some of the modeling that we do in the compiler and how it relates to TTNN. So we have the primary mesh attribute, which is very similar to the mesh attributes you saw in the previous slides. We have a mesh name and the mesh shape. We are able to provide multiple meshes and potentially compile various parts of our model, various parts of a graph on different meshes. But for now, we support a single mesh compilation. We have a mesh shard type attribute. This basically defines how a tensor should be sharded, replicated, or concatenated on your device. So there's 4 different types of this attribute. We have an identity, which basically means our input and output tensors are already pre-sharded, so we don't really have to do anything. The second is replicate, so we want to actually replicate this tensor across all devices. We have maximal, so we want to put this full tensor on one or more devices on our entire mesh. And then we have devices, so our tensor is actually sharded across the entire device. We have the mesh shard direction. Are we going from shard to fold or fold to shard? Very similar to your mappers and your composers abstraction. And we also have a tensor mesh sharding axis attribute. Essentially, this is very similar to the tensor dimensions that you had to provide in your mapper and composers. So here, let's say if you have a mesh of like 2 by 4 and your tensor rank is 4, we can have a shard shape of 1, 2, 1, 4, which basically means that your tensor dimension 1 over here and your tensor dimension 3 over here are going to be split across your 2 by 4 mesh on each of these 2 axes, as you see. So for those of you who have used MLIR, this should be something that you've probably seen before. For those of you who haven't, essentially MLIR provides a way for us to do analysis and abstract operations, do conversion passes, etc. of a graph and application, ML application. So this is basically what the generic structure looks like. We have a root module, which contains a bunch of functions that you want to execute. We have a bunch of arguments that we want to pass through, a bunch of operations that we execute, and then the return return results of the function. So here we have a module attribute that we append onto the module. This is the same mesh that you saw on the previous slide. Here we have a mesh of 1 by 2. We have a special op called a mesh shard op. What the mesh shard op does is effectively it takes a input tensor. So in this situation, our arg0 input tensor, and it's going to either replicate, split it on device, or concat it from the device. In this situation, our arg0 tensor has shape of 1, 132, 128. We see that our shard dims have a -1 value, which basically means this we're going to ignore that, and a 3 value, which means that the tensor dimension 3 is what's going to be split on our mesh. We can see the shard shape of mesh 2 over here. So that means that this dimension, third dimension of the tensor, is going to be split on this mesh axis. And we're going from full to shard in this situation. So our input tensor, effectively, once it's split, is going to have this shape where the 128 got divided by 2. Similarly, this is just the reverse direction. So in this situation, we're going from shard to full. It has the exact same shard dims and shard shapes. And in this situation, we have this tensor dimension of 3264. It's going to be combined into 32128. And you can kind of reason about how this would get translated into the composers and mappers in TTNN itself. Okay, great. So we went over how our Tenstorrent representations kind of look like. However, the great thing about MLIR is its concept of dialects. Dialects are kind of like namespaces where you can abstract namespace-specific operations and attributes and etc. Tenstorrent, our TTMLR compiler has primarily for multi-device, we have 2 dialects. We have the TTIR dialect and we have the TTNN dialect. Stable HLO is part of the OpenXLA project, where they also have a specific dialect and a specific set of operations. And what we do essentially is we write conversion passes from Stable HLO into our TTIR dialect that gets converted to TTNN. And then finally, the TTNN dialect will actually execute what needs to get executed using the TTNN runtime library. So Stable HLO essentially also has the multi-device representation, something that the first kind of representation was called GSPMD. So this is also very similar to some of the stuff that you saw already with the mesh composers and the mappers. We have this couple of custom operation calls that they have, SPMD full to shard, SPMD shard to full. They have a bunch of other annotations, so num partitions, like very similar to your num mesh, so how many devices that you have, and other stuff that you can append onto your graph. And here's kind of a link of the GSPMD paper and the reasoning of why it was created in the first place. So this is essentially what the MLIR graph looks like for Stable HLO. Once again, kind of similar structure to our TTIR graph, since it's in the MLIR infrastructure ecosystem. The main things to kind of point out over here are they have the MHLO num partitions and num replicas. We had the mesh in our example. So here you can see that in this situation, they are taking this tensor over here, 8192 by 784. They have devices of this mesh over here. They're going to split the second dimension over here, as represented over here, across the 2 devices. So effectively, you're going to get a split tensor dimension of 8192 by 392. And on the flip side, you are going to compose these together. So in this situation, we're going from shard to full. We have this tensor shape, and that's going to be combined together into the original tensor shape that we had. So what we do is we take the Stable HLO graph, we have a conversion pass that gets run, where we analyze all of these ops in Stable HLO, and then we convert them into the respective mesh shard operations that need to get executed in TTIR. And then once it's in TTIR, we have the conversion to TTNN, and then TTNN will actually call the runtime APIs. So yeah, similarly here too, we have the shard to full situation gets converted into a single mesh shard operation. All right, just a quick recap. Like you can see before, we have SPMD full to shard into our TTIR dialect that's represented by a mesh shard, into the TTNN dialect, which is also represented by a mesh shard. And this is all within the compiler. And then that will actually call the runtime, which is in TTNN, depending on what mapper it needs to run, does it need to get replicated, sharded, etc. And then the same situation for shard to full. all the way down the stack into the runtime APIs. There's a couple more APIs that we also use, but this is just to kind of show you how the flow actually works, the interaction between the compiler and the runtime works. All right, any questions so far? Okay. All right, so the next is our collectives. We went over the TTNN library collectives. Stable HLO also has support and representation of their CCL ops. So they define 6 CCL ops in the Stable HLO dialect: all gather, all reduce, reduce scatter, collective permute, all to all, and collective broadcast. We currently support 4 of these, but these 2 ones are still a work in progress. And if you want to see the full specification from OpenXLA, you can check out this link. So essentially, the goal is we have a Stable HLO representation of the all gather. We want to write a conversion pass into TTIR and then to TTNN, and then get that executed on our device. So in Stable HLO, they primarily have these 2 attributes that we query. We have the all gather dimension, which is the tensor dimension that you want to perform the concatenation on, and replica groups, which consists of groups of devices that are going to participate in the all gather with one another. In TTIR, we basically propagate this entire all gather dimensions down the stack. However, for replica groups, we convert it into a cluster axis, which defines what axis of your mesh is going to, and those devices on that axis are going to participate in the all gather. So over here in TTIR, you can see we have an all gather dimension for this particular tensor, the cluster axes. Here we have the input tensor, which has 32 by 64. We're going to perform an all gather on the cluster axis 1, so 2 devices. So essentially, we have a final tensor of 1 by 1 by 32 and then 128. Similarly, for reduced scatter, the Stable HLO representation has the scatter dimension, which is the tensor dimension you want to scatter across devices. Replica groups, which is just the groups of devices that are going to perform the reduced scatter on one another, and the actual reduction type, so summation or whatever other reduction type you want to perform. We basically propagate all this information down the stack, very similar to the all gather. And the representation is also pretty straightforward. Cluster axes, the reduced type in this situation is sum, and the scatter dimension in this situation is 3. So here we have this tensor. We want to scatter across this dimension over here across 2 devices. So the final tensor, or the sharded tensor, is going to be 1 by 128 from 256. And then finally, we have all reduce. So in this situation, we use the all reduce in representation of Stable HLO, replica groups, computation, very similar to reduce scatter into TTIR. TTNN still is in experimental mode for their all reduce support. So what we do is we basically split this all reduce into a reduce scatter and all gather, which effectively mimics the underlying operation that all reduce does. So it is a performance hit, but once they have their TTNN all reduce first-class citizen support, we should be able to remove this completely and have a direct one-to-one translation between these 2 layers. And then finally, collective permute is the other Stable HLO operation that we support. So in this situation, what collective permute does is it takes a shard that lives on one device and it'll send it to another device, so a point-to-point communication, and that's represented by these source target pairs. So over here, you can see that we have 2 devices. We're going to take the tensor shard that lives on device 0, send it to device 1, and the tensor shard that lives on device 1 and send it to device 0. So you can create kind of pipeline parallelized models using this approach. And we basically we basically represent this as this particular attribute all the way down the stack. So TTNN is still currently implementing send and receive, so point-to-point communications. So currently what we do is we basically bring this tensor onto the host, and then we remap it depending on where the shards need to go for all the devices. But once both these supports are in, we should be able to replace the current host fallback for now. All right, any questions? Okay, I see. Do you have tools? How well the tools algorithms perform? So I know there's a bunch of performance analysis that the TTNN guys do on their end. So if you actually want to test specific CCLs and how well they perform, it would be primarily on the metal side, so the metal library side, but not for, we don't have currently anything in the compiler that does this. We do have the similar performance library that Metal uses. We also do have in the compiler itself, but that's more on an op level. So like if you execute an op across multiple devices and you do some CCL, it can tell you the duration of the kernels and stuff. But to actually perform the algorithm standalone in like kind of like a micro benchmark, that would be something that the TT Metal guys would be more familiar about. All right. Great. Awesome. So at this point, you probably are wondering, hey, this was great. We have all the compiler stuff. We know how to write MLR graphs. We can get that converted into TTIR, into TTNN, and run it using TTNN library. But how can I actually use it from maybe like Torch or JAX or some kind of front end? So our primary multi-device support for now is through JAX. What's great with JAX is JAX has first-class citizen support for a lot of multi-device constructs. So and also JAX emits Stable HLO, so it works really well for us. So some of the core concepts in JAX that kind of we use and we build a bunch of test models, graphs from are as follows. So we have the JAX mesh, very similar to the mesh stuff that you've seen up until now. We have something called the JAX sharding partition spec. This is how do we want to shard a tensor across its dimensions, and how does it relate to the mesh that we're sharding across. We have something called the name sharding. So it's mapping a partition spec with a mesh that we have, and then we can actually shard our some type of array or a tensor according to what the name sharding is. So using this, you can shard your tensors, you can replicate it, et cetera, so forth. And then they also provide other really great functions. For example, the shard map function that allows you to take any function, provide some input specifications, output specifications, and when you JIT compile the graph, it will actually compile and annotate the graph accordingly for you. Anyone who's more interested in this, they have fantastic documentation on their website. So I will definitely leave, I've linked the documentation down below. Let's go over an example of how can you write JAX code, how does it translate into Stable HLO, TTIR, and then finally, how does it run on our device? So let's take a very simple example over here. We have a 1x8 mesh. This is a LLM box. We can annotate the axes of our mesh. So this is just annotated as 1. And then the batch dimension is going to be annotated on the 8. We're going to create a tensor over here. It has a shape of 8192 by 784. And then we're going to use this the shard map API that they have to compile, JIT compile our model. So over here, what we do is we create the shard map, the mesh attributes, in specifications, out specifications, and what the operations that we're actually executing in the model itself. So let's go step by step as to how different parts of this graph are being translated into the graph. So primarily, we have a JAX mesh. Here, we create the mesh over here, and then in the Stable HLO, it gets represented using the partitions and replicas that I showed in the other screen. And using the partitions and the replicas, we then write conversion passes, and we're able to analyze the graph and figure out, hey, this is a 1x8 mesh. Then we have the input specification, specifications for how the inputs should be sharded. So in this situation, we have a partition spec and the input, so 8192 axes is being split on the batch dimension over here. This will get translated into a SPMD full to shard, which completely happens on the JAX JIT side. And then all we have to do is similar to before, write the conversion pass from SPMD full to shard into our mesh shard, which exists, and then we can actually convert the mesh shard into TTNN and then run it on the device. You can see the all gather over here. They provide mesh axes you're actually going to perform the all gather on. So which devices are going to perform the computation with one another. it gets translated into a replica group. So we have 8 devices because we're on the batch dimension. So these all devices are going to do an all gather on one another. And then that gets translated into a cluster axis. So we analyze, hey, oh, it relates to this axis in our mesh, and that's what we want to perform the all gather on. And then finally, we have the axes. This is the tensor axes that we're going to actually do the all gather dimension on. So that's just a pretty straightforward conversion into Stable HLO and then into TTIR. Oh, and sorry, and then finally, we have the output specification. So this is very similar to the input specifications. It gets converted to shard to full, and then finally a mesh shard. All right, any questions so far? Okay. So at this point, you might be asking me, well, this is also great, but is there any way that the compiler can do more to kind of help us out? For example, GSPMD style annotations are a little difficult to read, especially as the model grows in complexity and size. Manually annotating the entire graph can become extremely cumbersome as well. And the compiler, at the end of the day, should be able to kind of solve the graph for you or provide hints. If you provide some hints or at least produce some optimized results. And that will lead us to something called Shardy. So to set the stage for motivation, we have 2 input tensors. They are going to be added together. We're going to create an output tensor. We want to split this computation across 2 devices. Now we can manually write some mesh shards over here, write a mesh shard here, and then write a mesh shard here to do some concatenation. But this is extremely tedious. This is just one op, but let's say you had like 100 ops or 1,000 ops. It's very difficult to figure this out. As well, add is pretty simple, but if you have reshapes, broadcasts, convolutions, it gets a lot more complex. So in comes Shardy. This is all credits to the Google DeepMind team. So instead of performing an analysis on the tensor dimensions, we can decompose the dimensions into one or more factors. And then we actually perform the analysis of how things should be sharded, how sharding should be propagated to and from ops and within an op. And then we can relay the propagations back into the original tensor dimensions. So Shardy is essentially a compiler framework that we can use in order to actually run analysis on our applications. We can either use partial annotation, so user can partially annotate their graph of how they want specific tensors to be sharded. Shardy can solve it, or we can kind of figure out automatically how things should be sharded and in which way. So to give you a very simple example, Shardy, this is a Shardy MLIR graph. You can annotate these Shardy functions onto any kind of dialect, and we annotate it into our Stable HLO and TTR dialects that we use in the TT-MLIR stack. Shardy mesh, very similar to what you've seen before. And then you can also annotate a sharding attribute to your tensor. So this is saying, hey, this dimension of my tensor is going to be split on batch. So 64 is going to be split on batch. And then 128 is going to be split on default, which is just 1. And then once you actually do the sharding propagation, here we have a Stable HLO CBRT operation that's being done. We want to know what is the final sharded annotation of this particular operation. Visually, we can kind of determine it, but once you have like many ops, it becomes difficult. So once you actually run the passes that Shardy has, it will go through every single op and it'll annotate it for you and say, hey, this operation is going to have this particular sharding annotation once it's been resolved. So how does it actually do this? Well, essentially, how I mentioned before, we're going to take the tensor dimensions, convert it into some factor dimension, and then do some analysis on the factors, and then project it back into the tensor dimension. And this requires every op defining some type of sharding rule. So let's take this very trivial example. Let's take this Stable HLO.general. Here we have a mesh of batch 4 and tensor 4. We're going to perform a .general on this. The contracting dims are 1, 0 for the respective tensors. And our left-hand sharding, we're going to annotate with batch and tensor. So our left-hand, this guy over here, this 8 is going to be annotated with the batch. And then this 32 is going to be annotated with the tensor. We also define a sharding rule. We say, hey, our inputs are going to be our input dimensions are going to be decomposed into these factors. So this 8 has a factor of I, 32 has a factor of k. This 32 has the same factor of k since these two are being multiplied with each other. And then we have a separate factor of j for 16. And the resultant tensor is going to have only I and j since k factors will not exist anymore. So to kind of summarize the slide, essentially what we do is we propagate the sharding dimensions across the factors. So factor I had initially a sharding dimension on batch. So we're going to propagate that to the result because there is an I that exists in the result. So over here in our dot product, we have a batch in the I place. The factor of tensor was the tensor sharding was on factor k. However, k does not appear in the final output. So that's why we don't have any tensor dimension sharding in the output. So we can see that this operation basically had its input sharding on the left-hand side, the right-hand side, and the operation produced a output sharding of this particular type. So if you annotate all of your tensors, all of your operations with a particular sharding rule, you can basically partially shard your graph and then run the Shardy passes to kind of solve the graph for you. What's great is Stable HLO guys have already done this for us. They've basically written all the sharding rules for many of their Stable HLO operations. So what we do internally is we hijack the Stable HLO operation. We kind of write a we partially annotate the graph, some batch dimensions, etc., run the propagation passes, and then we're actually able to solve the graph and then propagate the rest of the graph down to TTR and TTNN. Yeah, and to kind of summarize what some of our future goals are, so we're expanding support on Torch side via the Torch XLA kind of path. We want to do more automatic parallelization via Shardy, since Shardy has quite extensive support on this front. We're also manually writing a bunch of manually sharded models. There's a lot of bounties that are available, increasing support for collectives in compiler runtime, different parallelization strategies, and also extending multi-chip to Forge front end, one of our other front ends. Yeah, that is it for the presentation. Yeah, thanks, guys.